Welcome everyone to another webinar by DevOps.com. And before we get started, just want to tell you a few things. First, if you have questions, just look in your control panel. You'll see a place to put the questions. You can ask questions throughout, and we'll try to answer them all at the end. Any we don't get to, will be replied to personally. Secondly, if you have any issues with sound or quality, use your chat and send out a little message to us saying, hey, I can't hear, or I can't see, or something's wrong. With that said, we have an interesting webinar today with Mesosphere. And we've all been through a lot of transition with DevOps, and DevOps continues to transition. And what Mesosphere has done is found a way to automate Kubernetes, which is probably the hottest container product out there. And the person to walk you through that is Chris. Chris, let me turn it over to you. Why don't you introduce yourself?
Thank you. My name is Chris Gaun, product manager for Kubernetes here at Mesosphere. And today we're going to be talking about DevOps in the age of Kubernetes, or how DevOps is changing in the age of Kubernetes. So again, my name is Chris Gaun. You can follow me on Twitter. Actually, I think it was on the last slide at Gaunettes. Let me just go back. Oh, no, it wasn't on either slide. And I'm the product manager here at Mesosphere for Kubernetes. And I'm a Kubernetes expert. I'm a CNCF ambassador. CNCF is the governing body of Kubernetes and a bunch of other cool projects like Envoy and what's another one? Prometheus for monitoring. Previous to this, I was an analyst at Gartner, where I covered public cloud like AWS, Azure, Google. And I've been in the Kubernetes community for a fairly long time. Kubernetes is a 4-year-old project, meaning both GA and beta. So almost the entire time it's been in GA, which I believe is about 3 years, I've been involved in Kubernetes in the community, speaking about Kubernetes throughout the world, giving sessions and trainings on Kubernetes. If you're interested in talking more, syncing up, you don't want to do it through Twitter, we have a Slack channel, a DCOS Slack channel for Mesosphere. You could just ping me directly or DM me directly. It's chrisgaun.mesosphere. Or if you want any more information, you could talk in general, or if you have specific engineering challenges or questions when you're implementing Kubernetes on DCOS, you could go into this channel, Kubernetes, and our engineers are in there. Our lead engineer, you see his picture there, Pierce, he's actually always in there. If I have questions, I actually go into the DCOS Slack. The other thing that you could do to get started is if anything interests you, I always like to kick the tires, right? And so we set up this GitHub. You could just Google search Kubernetes DCOS Quick Start, and you'll come to this. Probably the first link will be to our Quick Start guide. And with a few make commands, you could get the newest version of DCOS and the newest package of Kubernetes up and running on your choice of cloud provider, AWS, Google, or Azure. And it's very simple and easy to do, and it's open source, so all free. So today, the topic is about the evolution of automation management, or DevOps versus site reliability engineering in the age of Kubernetes. And this is an analogy I borrowed from Eric Schmidt, the chairman of Google. I saw him talk about this a few years ago at one of his keynotes that he was doing at some conference. And he gave the analogy of, when cars first came out, you had to go out of the car, you had to crank the engine to start, you had to go back into the car, you had to shift it into gear, and then you had to drive to point A to point B. And technology has been automating stuff in the car industry. So right now, when you go into a car, obviously you turn the key, or sometimes you could just press a button now, like I have in my car. We now don't shift into gear because we have automatic transmission, which makes it much easier. And then in newer cars, you could even have it drive you from point A to point B. Now, all these are abstractions. So turning the key is abstracting the crankshaft or whatever, the engine starter that's there. The automatic transmission is abstracting the shifting of gears. So you as a user are being more and more abstracted to the value that you find from a car, which is I just want to get to point B, get me there, and not worrying about the minutia of shifting into gear, turning key, and so on and so forth. And our data centers are transitioning in the same way, right? We used to have the plug-in servers and set them up, and then set up all the networking. You can now do this through cloud providers or through your own virtualization or cloud software. And then once that's up and running, you can then automate the provision of applications stacks, which we used to do with configuration management tools like Chef and Puppet. But there you were still worried about the environment and the versioning and variables such as that. Now, in the age of these container orchestrators, we want to get to the point where it's purely declarative. So just like you're saying, drive me from point A to B, and you don't care exactly what's going on underneath. With container orchestration, with software-defined network, you want that same level of abstraction, where you say, you know what, I just need 3 instances of this pod. You figure out the best infrastructure to run it and keep it up and running. And that's the level of abstraction that we're trying to get in our current data center. And it's finally at the age that we're there. Next slide. So how did we get here? I mean, in the beginning, there was the mainframe, right? These huge metal computers that filled entire rooms and cost millions upon millions of dollars. They were very efficient. They ran actually at utilizations above 80%, but obviously, no one could afford them except for the very large organizations, and it took a group of people in order to maintain it. But from there, we got our traditional applications or legacy applications that you might think of now. Or maybe not legacy. You probably still build applications in this model, but the way that it works is that you have the application, and then you have the operating system, and you have your hardware, and all the application components on a stack. And so everything is tightly coupled. And there's no decoupling or 2 pizza teams or teams working together. Everything, if you change one component, you're basically changing everything underneath. So this is a highly coupled, large application with many layers of coding. But then things got smaller, right? We transitioned from the mainframe to the personal computer. And then things got connected. So each one of these clients actually got connected to each other, and then through a larger network and the internet. And then they scaled, right? We didn't just have a few servers that we put in. We now have, probably in Google size, million+ servers that they're handling all throughout the world. But then the problem with all that infrastructure is, how do you actually build an application or processes that could take advantage of it? These are servers that are dying all the time. They're commodity. There's many of them, again, distributed throughout the world. So we actually had a revolution in distributed applications as well, or distributed for the distributed infrastructure. And an early example of this is actually Hadoop, which came out of a research paper from, I shouldn't say came out of a research paper, but there was originally a research paper that came out of Google about MapReduce, a concept for distributing these workloads on this commodity infrastructure. And this was used internally in Google to do batch processing or work on jobs. And that was one of the earliest examples that we have of modern distributed applications. And from that, it actually came, the paper was written, and a few people actually came up with Hadoop, which is an entire ecosystem of tools to mimic that MapReduce logic that they wrote about in the first paper. But the problem still existed that you had these distributed systems or these distributed applications or these distributed data stores, but they were static as far as the partitioning goes. So you had some servers that were dedicated to Hadoop, some that were dedicated to Memcache, some that were dedicated to Cassandra and MySQL, and so on and so forth. You typically did not have workloads that were operating like on the same infrastructure, or you weren't having infrastructure jump from one workload to another. And so again, you had the static partitioning of Hadoop and other workloads that you're running, and then you typically want to get to this model where you have dynamic resource sharing with a shared cluster. So you also have virtualization. Everybody knows what this is, where you have VMs, each with their own operating system, and a hypervisor underneath for the hardware. And this was a way to converge not just the infrastructure that you now have distributed across your data centers. And then a new movement that we've seen in the past, I would say 5 or 6 years since Martin Fowler, I don't know if he coined the term, but he definitely made it popular, is this microservices approach to building applications. And in this microservices approach, you're building an application where each module supports a specific business goal and uses a simple, well-defined interface to communicate with other modules. Oftentimes, you say that you can build these with 2 pizza teams, and they're independent of each other. They're flexible, they're resilient, they're robust, and they're scalable. And that's one of the more important things and aspects as we move into cloud, as we move on to containers, as we move on to Kubernetes. We want to not just deliver those monolithic applications where changing a component changes everything on the stack. We want to deliver a better way of doing distributed applications where I could have some teams working on particular components or particular services within the structure, and then update them and have them just work with the other services that other teams are working on. So the other characteristics that you see of microservices are they're polyglot, they use many languages. They have a single responsibility, whether it's for data services or whatnot. It is not like a monolithic application where it is doing the data services and the business logic all in one place. And then again, you have the 2 pizza teams, smaller teams. So a team that you could feed with 2 pizzas. I keep on saying the word 2 pizzas, but I haven't explained what it was. So that's what they mean by 2 pizza teams. And then you want to be able to have high utilization and avoid the dependency hell that happened in the ages where we were completely dependent on monolithic applications. So in the past, what has been 4 or 5 years, containers has been a hot topic because it has been a good way to package applications and deliver them in a very formalized way. So here you can take your application, you can package it up in a container and actually just run it on any operating system that supports that container or supports that container runtime. And this makes it easy to deliver, but it also makes it easy to scale because containers are incredibly fast and easy to move around. So the idea with containers is that we want to achieve rapid deployment. We want to have the container image in a repo so that we could easily access this for later. So we want a single golden image of each container that we have in an image repo that we can then deploy to the infrastructure. And typically when you're just starting out with containers, you're doing something called like spreadsheet scheduling, which means that you're handling all the scheduling of the containers yourself, but that's not good enough. That's actually not going to work when you start to have 10, 20, 30 containers or more. So that's where container orchestration comes in. We start to get 10, 30, 100 containers. You have this Cambrian explosion of containers out there, millions of downloads, probably billions at this point of Docker containers. And you want to not just have the container scheduling, which is the ability to distribute these containers throughout your distributed infrastructure, but you want to have the resource management of, having the correct CPU and memory, and making sure that containers are confined to, say, the namespace that they need to run in, and then service management as well, so that the containers can actually communicate with each other, or you can discover them. So with container scheduling, it's the placement of the containers on the infrastructure, the rescheduling, so if something goes down, for instance, the upgrading of containers, the downgrades, the co-location, so multiple containers per VM or per bare metal server, and then your rolling deployments or any other type of deployment or scheme that you want to do, blue, green, canary, that's what's handled by the container scheduling. The resource management is the memory, CPU, GPU, the sort of cloud infrastructure resources that you typically need in order to run anything nowadays. And then services management is the labels, the groups, the namespacing that's needed in order to manage these containers at scale. So again, this is a layer cake model where you have your web apps and services, and I would say even packaging mechanisms for these applications, like a Helm chart. And then you have service management, which is the management, the namespacing of the container orchestration, and then the scheduling, which is moving the actual applications around, and I would say even the orchestration of the containers, and then the resource management, which is the raw CPU, GPU, and getting that to the container orchestrator. So that's container orchestration. So, one of these companies that has been solving container orchestration and actually originally contributed C groups, one of the primitives for containers into the Linux kernel, is Google. And Google has done this because, just like with the MapReduce algorithm, they operate at enormous scales. They have over 30,000 developers. They have 40 engineering offices. They have 800,000 builds per day. That's just mind-boggling, right? This is like, nothing that we mere mortals typically see in our data center. And then 2 billion lines of code if you're actually counting Google as an operating system. And so one project that they open sourced, again, it was 4 years ago and probably 2 weeks at this point. It just had its 4-year birthday, is Kubernetes. Now, they did this is because they were actually managing 2 billion containers internally per week, or starting 2 billion containers per week. Now, these are ephemeral containers. They're not lasting for a very long time. You typically, spin up a container, they might last seconds or microseconds, to be honest. But they do have that, 15 plus years of container orchestration, research and development. And they learned many, many lessons while doing that. So they have these systems internally Google called Borg and Omega, which they use to manage sort of, you could think of it as like the Google operating system. And so from that, they learned, lessons on what they would like to have if they were going to, build a separate container orchestrating system that just handled the containers. And they also have distributed systems DNA. So C groups, which I mentioned, they originally contributed those to the Linux kernel. Artificial intelligence, which is a distributed system. TensorFlow is extremely popular. That's a deep learning framework that's out there. MapReduce, which we already talked about, and Bigtable, which we didn't, but that's actually, originally where it was a paper or an idea where some of these distributed data stores that we are now seeing come from. And so that's where Kubernetes came from. And actually they open sourced it, and there's many vendors involved in the Kubernetes ecosystem. This is not a Google product anymore. It's actually now governed by the CNCF, the Cloud Native Computing Foundation. And today we'll be talking about how we operate Kubernetes on DCOS and how we actually automate the management of it. But before that, I want to talk about this ancient time, because we talked about the actual orchestration of containers. A lot of them are stateless. Up until a few months ago, Kubernetes did not have any stateful sets, and still local storage is in beta. But I wanted to talk more about the data services that we've seen, the distributed data services that we've been using in our data centers for the past almost decade at this point. And so in ancient times, there were things like MapReduce, which we already covered, which was crunching data in a batch processing type way. But today we need something faster. We need to churn out data. We're connected with our phones and in every other imaginable way to the internet. We expect a different standard when actually interacting with an application. We want to make sure that, when I open Google Maps, it knows exactly where I am. It's giving me suggestions in real time based on, the street I'm visiting or I'm in, or another example is maybe if it's raining, I want to get in my in New York City, and I live in New York City. I want to get suggestions of, hey, maybe it's a good time to do a vacation from, say, the Delta application. I'm saying this because I'm sitting in a conference room in the Atlanta airport, so I'm just reminded of that because I just got one of those typical notifications that you see in modern applications. So how would you pull this off? How would you do this fast data? Now, in days past, you would do batch data. When I worked at Gartner, they have this internal system that's based on Lotus Notes and I believe an SAP database or something of that nature. I don't even think it's SAP, but you would actually put in your paper to be reviewed, and it would take 24 hours for the system to notify the reviewers that the paper was ready. And then after that 24 hours, they would be able to download the paper and then put their reviews into a Word document, and then re-upload it to the system. And then another 24 hours would go by for the batch processing. And that's where you would actually be able to see who reviewed your paper, what they liked, what they didn't like. So literally, the fastest it could be was 24 hours. And so that was the batch processing. That's the typical data warehousing reports type processing that we've had in the past. Now there's micro batch processing as well, and Spark is an excellent example of this. This is something where it's taking records in almost real time, in like seconds, and taking a batch of those and processing them almost as they come in. And then there's microsecond, like event processing. A Flink is an example of this, where it could take streaming data, say that's coming from Kafka, and actually process it in real time and actually output it in real time as well. And so that enables you to actually have these like real-time product recommendations or pricing and routing information, real-time advertising that I talked about, or just a predictive user interface, like what application do you want to see right now? So an example of Smack Stack, and this an example that works on the DCOS stack, is Smack. And what I mean by Smack is it's an acronym. And what we want to have for this type of fast data is we want ingestion. So we want to be able to get all these streams of data into our system. And we could do that through Kafka. And then we want to analyze those streaming data. And we could do this through either Spark or Flink. If we want micro batch processing, or we want it a little bit faster, we could use Flink. And then we want to store that result. So we need a persistent storage, preferably distributed so that we can reach it over a vast geography. And then we want to act on it. So Akka is a way to visualize the data and build data-driven applications. So that's the Smack Stack, and it works on DCOS, and I could show you an example of that later. So what's the challenges? So we talked about this a little bit. if you were going to go and say, I want fast data, I'm sold, this is, something I want to build this, machine learning pipeline or whatever it may be, you're still probably going to provision it in a static siloed version. So you would set up some servers for Spark and some servers for Cassandra and some servers to serve it in Kubernetes, and then some servers for CD, for Jenkins, and so on and so forth. What we want to be able to do is actually converge that into a hyper-converged infrastructure where it's all shared. And so the reason that you don't want this is because, deploying, scaling, configuration, recovery, it's just the same nightmare. It's a different, it's a different configuration management script for each one of these servers or each one of these environments if you're doing it over cloud and your private data center. And you just don't want that 3 a.m. beeper to go off or call where something goes down and you need to go fix it. And it's almost like solving a murder mystery because you're not sure where it happened or how these are connected. And so that's the problem with doing it in just a single environment. You could imagine doing this over multiple environments or multiple data centers if something goes wrong. And actually, how do you actually distribute this across multiple data centers? That's where the real headaches and the real frustration comes in. So introducing Apache Mesos that helps solve this problem at Twitter and other places. So Apache Mesos, and you can follow this link, is a data center kernel. And what does it mean by that? So it's a building block of the modern internet. It's a cluster resource negotiator. So it's offering up CPU and memory to different schedulers like a Kubernetes so that they could feed themselves and say, oh yeah, I could run this many worker nodes with this amount of CPU that's being offered up by Mesos. It's a top level Apache project. It's scalable to tens of thousands of nodes. So originally, one of the best use cases or case studies was from Twitter, where you would actually see this the fail whale if you used Twitter 10 years ago. And Apache Mesos was part of the solution that helped kill the fail whale. So it was able to scale the infrastructure in a way and manage it and keep it up and running in a way that previously wasn't possible. It wasn't possible with configuration management, standing up each instance of the data services of MySQL just wasn't going to cut it. They needed a better way, an automated way in order to manage everything. It's fault tolerant and battle tested. Again, it's used by an incredibly large organization to build basically their data center, their operating system. The operating system of Netflix partially runs via Mesos, and that's how they're managing their container orchestration solution. So what Mesos fundamentally does is it does multiplexing of data, services, users, and environments. So it takes these static stacks of Spark or Hadoop or Kafka or Kubernetes and Cassandra, and it consolidates this into this high density infrastructure where it's all being shared on the same servers, virtual machines, or public cloud providers. So Mesosphere, with its product DCOS, helps business navigate digital transformation in hybrid cloud. DCOS is powered by Mesos. It enables us to ship more applications quickly, or our customers to ship more applications quickly. So getting that Spark service is incredibly easy to do. It's a push button. It takes 5 minutes in order to get up and running. And then it's the management, the ongoing day 2 management of Spark is then completely automated. So we'll have this example with Kubernetes. If a worker node in Kubernetes goes down, you don't have to do anything as an operator. It just comes back up and running without any effort on your part. And it helps you capture the value from real-time data. So you want to be able to be the enabler of fast data to any group that wants to use it, or a machine learning stack or deep learning stack. You want to be able to spin that up in a repetitive and consistent fashion and manage it on an ongoing basis. And DCOS enables you to do that. And then in modernized enterprise architecture, so it's going to pool all the resources that you have, all those servers that you have, into a single infrastructure fabric and help feed these modern schedulers, these modern distributed systems that you need. Mesosphere counts 30% of the Fortune 50 companies as customers and 5 of the top 10 banks. We also have 5 of the top 10 telcos as customers and 5 of the top 10 most valued startups. So what we want to do is take the new levels of complexity that we talked about when you're doing fast data or any type of microservices application, which will always include transportation, so getting data from your device to your data center, which you could do through streaming, like through Kafka, and then storing that in a distributed manner, which you could do through Cassandra, and then analyzing that in a process that's going to take not days, but seconds, which you could do through Spark, and then serving the results of that, those results through container orchestration, which you could do through Kubernetes. So this is the architectural diagram of DCOS, and we have broad workload coverage, so not just Kubernetes and all these fancy data stores, distributed data stores, but also J2E applications. Your old school Java applications will run unchanged, not Dockerized, on DCOS. And then analytics and machine learning, we have an excellent demo of that. If you go to our GitHub repo that I pointed out earlier, there's demos that you could go through when you're actually deploying the cluster. And then it has application-aware automation. What I mean by that is that it knows how to set up any of these packages. So when we're doing Kubernetes, for instance, it needs to be set up in a particular order. You need to do the etcd servers, which is the key value store, the single source of truth of Kubernetes. That needs to be set up first. And then the master nodes, those come second. And particular components of the master nodes have to be in an order. And then lastly, you could do the worker nodes. And so DCOS has a logic and has the ability in order to build these very complex or sophisticated systems in a way so that you could get them up and running in an automated fashion. It takes your run book and takes those O'Reilly books and makes it into a single command. And then intelligent resource pooling. So this is the high density infrastructure that we talked about before, where you could be running Spark plus Kubernetes plus Kafka, not all on the same DCOS instance, but all on the same infrastructure. So you could actually have, a kubelet, a single kubelet of Kubernetes being shared with Kafka on a node. So you have this high density, incredibly efficient, 80%, 90% utilization is typical on DCOS. And then unified hybrid cloud operations. So you can install DCOS on many different data centers in 2 models. One is linked clusters. That's where you have multiple instances of DCOS. Maybe one is in, say, AWS West, and then one's in your private data center. But they're too far apart. The latency is too far apart, so you have separate masters as well. The AWS cluster has a master, and then the private data center have a master. But you can still link them so it's one unified view within the UI. But you could also run DCOS with a single master across multiple data centers. So you could have, for instance, one of our customers is actually deploying DCOS in their main data center. That is where the masters will be located. But they also have, sites distributed throughout their region of 30, 40, servers each. It's almost like edge computing. And they want to be able to actually have worker nodes on each one of these distributed sites and manage it all in this, connected fabric. And that's how they're rolling it out. And that's true hybrid cloud operations. So DCOS with Kubernetes, again, I'm the product manager for Kubernetes on DCOS. So what value does DCOS bring to Kubernetes? Well, Mesos, as I mentioned before, automates Kubernetes. Not just getting the first provisioning of Kubernetes, like the single command, that's great, but the ongoing life cycle. What do you do on day 2 when something goes down, or you need to scale Kubernetes, or you need a new cluster? Mesos helps automate all of that, and to do this in a declarative method where I could just say, you know what, I want 5 Kubernetes worker nodes. I don't care where they are. I don't want to be in charge of monitoring them or managing them. I want to automate that as much as possible. Again, I am a driver. I just want to say, drive me to point B. This is my ultimate goal. Get me there in the best way possible. And that's what Mesos is doing here. It also enables you to deliver Kubernetes as a service. So multiple static Kubernetes on DCOS at this point. You could actually, in the future roadmap, have multiple high-density Kubernetes clusters, all sharing the same nodes on DCOS, a single DCOS instance. And then the entire CI/CD pipeline, the shared resource. So Jenkins, as a CD resource or CI/CD resource on DCOS, you can run hundreds of Jenkins servers on DCOS and manage them in the same way that you're doing Kubernetes. If something goes down, Mesos will make sure that's up and running and healthy. So layers of a Kubernetes solution. We got to remember where Kubernetes came from. It originally came from a cloud provider, which was Google. And when they were building Kubernetes to start, they made it very narrow scope. And there was 2 reasons for that. One was they didn't want to have the same mistakes as OpenStack, where it was just a gigantic project and it was just doing everything under the sun. They wanted to really just scope it to the containerized application orchestration, where it would do that really well, and then it would connect with integrate with all these other parts of the stack. And then Google, how they monetize Kubernetes is that they provide the as-a-service automation of Kubernetes. So the provisioning, scaling, self-healing upgrades. That's not in Kubernetes itself. That's some secret sauce. That's something that the cloud providers is doing themselves that you could maybe automate with a CloudFormation template or something of that nature, but you need something there in order to do it. And then infrastructure, it obviously provides the instances in order to feed all of this. So DCOS is doing something very similar. So it's using Mesos as the as-a-service automation for Kubernetes. So Kubernetes, again, is doing the container application orchestration. And what Mesos is doing is automating Kubernetes in the same way that Kubernetes automates automating Kubernetes infrastructure in the same way Kubernetes automates containers. So this gets me to Mesos' position in the container orchestration world. Mesos provides this intelligent resource management. So on the top, you have this container application. There's different ways to package containers, applications. In the Kubernetes world, Helm is one, Docker containers is obviously another. But then you have container management systems like Kubernetes, like Marathon, which are both available on DCOS. But there's other ones out there, ones that existed before Kubernetes or Marathon. For instance, Titus is one from Netflix, and they use that in order to operate or stand up 200,000 clusters per day. That might be a typo in their blog. I'm not actually sure. I don't know why you need 200,000 clusters per day. But in the blog, when they open sourced it, they said that they are using Mesos in order to stand up 200,000 Titus clusters per day and run 500,000 containers on those clusters, which is just mind-boggling. So that's what Netflix uses for container orchestration. And then YouTube and Twitter use something called Aurora, which again predates both Kubernetes and Marathon. And so there's at least 4 and possibly even more container orchestration frameworks, packages that work on Mesos at this point. And so what Mesos is doing, again, is orchestrating the infrastructure or managing the infrastructure of these container orchestration, like Kubernetes. In the same way, these container orchestration systems are managing applications or managing containers. And that goes into the different ways and how to actually manage Kubernetes. You can do it the manual way. There's actually a GitHub repo called Kubernetes the Hard Way by Kelsey Hightower, who's one of the most famous developer evangelists. He works at Google, and he's the foremost expert on Kubernetes. And so he wrote this guide on how to actually get Kubernetes up and running if you were going to do it step by step in a very manual fashion. And it is a nightmare. It is something that you would never do unless you wanted to know everything in and out of getting Kubernetes up and running. But just even, it's not even a full production Kubernetes cluster. It's just really a hello world of getting Kubernetes up and running. And it's something like 20-something steps in order to get a few worker nodes on your infrastructure. So you could go through it, but it's tedious. And there's no day two management. So if something goes down, you just have to, I guess, go back to the steps and follow up on them and reconnect everything. So there's DIY tools open source tools that automate this or some of this. Kops, KubeSpray, KubeADM are popular examples of this. These help you get a hello world of Kubernetes. The downside is that there's no commercial support. If something goes wrong, you pretty much have to put in a GitHub pull request or issue or go to their community hours that happen 2 hours on a Friday. It is a good way to kick the tires though. Security is also DIY in a lot of these tools. They typically use the defaults for the Kubernetes clusters. I'll get into why that's important in a bit. And then there's vendor configuration management tools. So this is something where you could actually get support for. It typically would include the auxiliary components. As a caveat though, those auxiliary components like say Jenkins or something of that nature, or the image repo is built into a platform that's sort of tied together. So although it does manage those components, they're not separated out. It's not broken down into the microservices architecture that we're trying to move towards. And then there's intelligent resource management. So you have the public cloud providers. This is something where you just write a single command, you get Kubernetes. If something goes wrong with Kubernetes, they fix it, or they try to. And DCOS and Mesos help us enable the same thing anywhere. So in your private data center or in the public cloud. So Kubernetes is only part of the solution. It's a very exciting part, but to really deliver agility in your organization, you need a lot more than just Kubernetes. You typically need an entire CI/CD pipeline, which would include the source control management from GitHub or from GitLab if you need to do it on-prem or wanted just an alternative to GitHub. It's an excellent choice. The building and testing solutions from Jenkins. GitLab also even has a CI/CD solution, and Spinnaker, which originally came out of, I believe, Netflix, one of the open source projects. And then the release of the image repos, and whether Docker or JFrog, again, depending on your preference. And then where you're going to deploy it to, again, Kubernetes or Marathon. And then you also have to monitor and have a way to look at the logs of these distributed systems, because you're not typically, if you're a developer and you're deploying to this, you don't typically have access to the infrastructure. So you need, robust logging to see what's going on. And the way that you do that is through Elasticsearch. The way that you monitor these clusters is through Prometheus. There's other ways to do it, but Prometheus and Elasticsearch are the open source and probably the most popular at this point. So what are the use cases, and how do you actually deploy Kubernetes when you get into production? Well, there's a few ways. There's a few topologies that you could use. One is the shared somethings, where you have a production environment that is shared, and you might have you still might have a few Kubernetes clusters for the production environment, just because of geographies or because of SRE reasons, you want to keep it up and running. But you're using the multi-tenancy and namespacing within Kubernetes to separate the applications or the services. So here you're assuming that it's trusted code. You're not, allowing third parties in order to provision applications to this cluster. They all typically have the same security profile. You don't want a highly secure application, sharing the same cluster as a consumer-facing application, for instance. And then, low compliance, low security. And then the developers typically have no access to this production cluster. And so you typically, in this environment, need to give developers their own clusters. You could do that through Minikube if you're satisfied with giving them just a single VM on their laptop, which probably will result in, oh, that didn't work. That worked on my laptop. Why didn't it work in production? Or more development cycles to make sure that it's working in a more realistic environment. Or you could give them their own separate cluster with a few nodes so that they can replicate what's actually going on in their production environment. And so that's the better way to do it. So each one would need a cluster with full API access so that they could truly test out their applications or build new applications. So that's the shared some things cluster. You could also have a shared nothing cluster or clusters where you have hard separation. So you're using, different Kubernetes clusters for each application, for each service. It's probably somewhere in between of these two, where you might have each business unit has their own cluster, but each business unit also has multiple services. Or maybe you just break it down by security profiles or staging or whatever it may be. But this is typically a mixture of the two is how you almost 100% of the time set up your Kubernetes cluster. You have, maybe 10 Kubernetes clusters per BU for the staging, and then each one of the BUs would replicate that. So each one would have 10, 13 clusters. And it just conforms to SRE best practices, to hard separation, so it's incredibly secure. Namespacing is also, when you actually have a lot of people sharing the same clusters that might not, agree on, for instance, when to upgrade the cluster, that could be a headache. And then developer environments are still the same. They would still get a cluster with full API access. And so why multiple clusters? Just to summarize, security and compliance. You're worried about noisy neighbors or nosy neighbors. So having two competitors on the same infrastructure, typically a no-no. You want to have full API access, so you want to give developers, again, a full robust cluster that they could use and debug. They would typically need something that's separate from everything else. Or it's just multiple independent workloads. An example of this that spoke at KubeCon in Europe a few months ago is CERN, where someone just wants to test some scientific data. They want to just spin up a Kubernetes cluster. They don't care about anybody else's lifecycle, and they just want to take it down. And so that's typically the case that you would see in a large organization. And then it's easier to manage the scaling. You're not just scaling the namespaces, you can just scale the cluster. The provisioning, you don't have to worry about anybody else if you're the only BU or the only application on it. And then independent lifecycles, and this is huge. Again, I can't imagine if you had tons of business units, each with, say 300 services on the cluster, and you say, oh, we're going to update everything all at the same time, or even just doing in one business unit at a time, it would just be a nightmare. So you need some balance between the two. And then also location. You can't have a Kubernetes cluster stretched across multiple regions with a single master in one data center. You typically need to have a federated model where you have multiple Kubernetes clusters, each one in each region. And so that's another reason that you would have multiple clusters. And so the shared everything model, that just hurts my brain. It's crying. It's typically not seen in larger organizations. You do see it, for instance, in places like SoundCloud, who has maybe 1,000 employees last time I checked, and maybe out of those like 100, 200 engineers. So it doesn't compare to Google, which I said had over 30,000 engineers, and a large bank, which might have tens of thousands of engineers. But they're delivering a single consumer-facing app or service, and with 200 engineers, you could probably share everything on one Kubernetes cluster for production. You probably still need one for dev test and one for your developers. The DCOS's goal is to be the run everywhere cloud provider for Kubernetes solution. So we want to be able to provide not just Kubernetes, but all the ancillary stuff that you need around Kubernetes to each one of the business units or each one of the users that need it. So if a developer comes and says, I need a cluster of Kubernetes, just test some stuff out, you could easily provision that and manage that all with a few commands. Today, we have multiple Kubernetes clusters on DCOS, but we want to, in the near future, deliver high density multiple Kubernetes. And so what I mean by that is we want to be able to have multiple kubelets per Mesos agent. And that will enable you to have, say, 10 DCOS nodes and a few 5-node Kubernetes clusters. And the reason that you would do that is because they're all just sharing the same infrastructure in the same way that Spark and Jenkins and GitLab can share the same infrastructure. And it would lead to extremely high utilization rates. And it'd almost be like some have talked about this nodeless model, where you are no longer worrying about nodes and the VMs that are housing those nodes. You can now just worry about your applications and just the holistic view of the cluster. And so with this, we're moving towards that nodeless model, where we're automating the kubelets, and the kubelets can be all shared on the same Mesos agent, the same Mesos node, and from there, you can see where this is going. So what's Kubernetes done right? So first off, it should be automated. We do that through Mesos. You could do that through a public cloud provider, but it should be as automated as possible. It should not be every time something goes down, you need to go and redo a configuration management tool. It should be evergreen, so it should be the newest version or close to the newest version of Kubernetes. This is so that it could be in compliance with other Kubernetes clusters out there. So typically the public cloud providers will be have the newest version a month after its release. So if you're choosing a tool, it should have the same APIs as the ones in the public cloud providers, right? If you want to have a hybrid cloud, it should be included. So it should not cost extra money for Kubernetes. It should be something that comes as part of a larger product or a larger solution. It should be open source. So it should not be a distro of Kubernetes where you cannot see the dividing lines of where Kubernetes starts and the distro ends. That is not kosher anymore. Maybe 2-3 years ago, we thought that was the direction that the market was moving. But at this point, pretty much all public cloud providers and all Kubernetes vendors are just using the pure upstream version of Kubernetes. And then unified, you need to have multiple Kubernetes is not an island. You need to have that entire CI/CD pipeline. You need to be able to automate and manage all of it in a single DCOS cluster. So with that, with DCOS 111, we have Kubernetes up and running. With that, you get highly available cluster provisioning, a single line, single command line, non-disruptive upgrades, auto repair, scalable Kubernetes, so it's very easy to scale it from, say, 4 worker nodes to 5 worker nodes, 6 worker nodes, 100 worker nodes. And with that, I'm going to just talk about a case study of machine learning, fast data. This is from Deutsche Telekom, and I thought it was very interesting. And what they're doing here is that they're using DCOS in order to manage their machine learning platform, their data science platform, their data engineering platform. And the reason that they do this, or the reason that they're doing this, is because customers can choose between hotspots or cellular networks, and it benefits both the provider, Deutsche Telekom, and the customer if they're choosing the right one. The customer is saving money because they're connected to a hotspot. Deutsche Telekom is saving money because it's expensive to build cell towers, and they want to make sure that the customer is having the best user experience and connecting to the fastest network. And so what they're doing is they're pulling in all this information, the speed data from cell phones in Germany, and processing it in real time on this machine learning platform. And they're using Spark, and they're using the SMAC stack: Spark, Akka, Cassandra, and Kafka. And they're also doing some classic data science, so going in there and seeing the results and sort of parsing them, or using a human to parse them. And they're using the ELK stack in order to do that. And this is all housed on DCOS. And right now, they're actually in a public cloud provider. They decided, in the future, we might be in several cloud providers. We might be in several cloud providers plus the data center, depending on how popular this is and how much we want to roll this out. And the application was delivered to market maybe 8 months ago. And in that time, it's gotten 16,000 reviews or close to it on the Apple iTunes Store, and 4.3 stars for a telecom app, a telco app. So it is extremely popular and extremely successful. And the way that they're doing all the analysis for this application is with a stack that's on DCOS. And so with that, I will now open it up to questions. If we don't get to the questions, then we'll get to you individually, so through email.
Hey, Chris, thank you. That was a lot of presentation. There was a lot of information there. I mean, I'm surprised you got through it within an hour. Everybody wants to know your Slack channel.
Oh, okay.
So
I will put it. It's all the way at the beginning.
Here. All right, that's so they know, because obviously you gave a lot, and they're going, we can't handle all this. And everybody knows that the webinar, you'll be emailed a link to this again, as well as it'll be available on demand on DevOps.com on the on-demand webinar section. So there are going to be copies floating around. But here, Chris, we don't have time for a lot of questions, but I got a real brain teaser for you. To build an application that scales to 5 million nodes, what would you do?
5 million nodes? I would.
Yeah.
I'd go look for a lamp to go rub and see if a genie comes out.
I thought that was a good one.
I don't know about 5 million nodes. So the largest infrastructure is probably Google. It's providing a single service, which is Google search. And there you probably, no one knows exactly, but it's obviously in the hundreds of thousands of nodes. And you have to do, we just talked about the container orchestration. In order to do that, that's one piece. And then the actual management of the container orchestration, that's another piece that you have to deal with. But then there's things like that you need to build, like having, making sure that the data is synchronized throughout the entire world. And to do that is not easy. You need to have quantum clocks, you need to have satellites, you need to have an incredibly fast network. You typically need to put down actual, cables under the seafloor. So that's the type of thinking that you need to have to get up to hundreds of thousands of nodes. So I don't know about 5 million.
Yeah, and I see a lot of questions we won't be able to get to, but understand, everybody, you can go to Mesosphere.com. I sent out a link twice that was talking about how you can schedule a demo for this, and talks more about the Kubernetes specifically within that area. And so I encourage you to go to Mesosphere.com to really get more, because this is not a topic that's going to be simple as you get into implementation. You need people like Chris that really understand the metrics and the dynamics of this. But I think that's really all we have time for, Chris. Do you have anything you'd like to add or say to everyone?
Yeah, I mean, please, I love hearing from you from either Twitter. Again, my name is Gaun on Twitter, or from Slack. You can see my name right there. Just send me a DM. I'd love to hear from you. Love to hear about what you're working on. Love to hear if you test out the product with this GitHub. Have feedback, features that you'd like to see in there. I'm the product manager, so please talk to me.
Yeah, well, thank you, Chris. It's been a great time today. And thanks to Mesosphere and Chris for putting up this webinar. And this is another DevOps.com webinar. Signing off is Parker Yates. Have a great rest of your day or evening or afternoon, whatever you have. Take care and bye-bye.
Thank you.